In this example, we'll draw the shear force diagram and bending moment diagram. But first we need to calculate the reactions. And we have a reaction here. And the other reaction is here. This is RB, and this is RA. So to calculate the reaction, we need to take moments about point A, for example. So sum of all moments about point A or B, doesn't matter, I'll do B, is equal to 0. So we have this will rotate in this direction, which is negative clockwise. This will rotate in this direction, which is counterclockwise positive. And as we said, the uniform load will be substituted with a force in the middle. Resultant, we said, this will be the equivalent of this force, and it will act at mid distance. This distance will be 20 divided by 2. So this will rotate also in counterclockwise, which is positive. So let's do the numbers. So we have minus RA multiplied by this entire distance, which is 30 feet. Then we have plus this one is 15 kip multiplied by this distance from here to here, which is 20. Then plus, open curly bracket and put the first is W is 3 kips per foot, multiplied by the entire thing is 20 feet, multiplied by half of the distance, which is from here to here, and that is 20 feet divided by 2 is equal to. So if you do the numbers, we'll get RA. Well, let's do the numbers. So minus RA multiplied by 30 feet plus 300 plus you have the total force will be 60 kip, and again I would say this foot and this feet will go, so I'll be left with kips. 60 kips multiplied by distance of 10 feet is equal to, so RA is equal to 300 plus 600 divided by 30 and is equal to 30 kips. So this is the first reaction. Now we'll continue. Do sum of all forces in y direction is equal to 0. So with this we have RA is upwards, this is downwards, this is downwards, and this is upwards. So these are the ones that will do. So we have plus RA minus 15 kips minus this one is WL plus RB is equal to. So the is equal to 0. So plus RA minus 15 kips minus W is 3 kip per foot, L is 20 feet, plus RB is unknown, is equal to 0. So we have, RB, RA, yeah, unknown. So RA, I should have substituted this. Because I already calculated this one. So this will be 30. So RB is equal to 45 kips. So I got these two values. So these are the reactions. Now so far I need always to make sure that you get the reactions right, otherwise the entire thing will be wrong. So if you go back to the previous two examples that we did, you will notice, and you have to keep this in mind, there's two cases. Well, one case was a point load, and for this we had the bending, the shear was, let me do this here. So we had a case of simply supported beam with point load. We have a case of simply supported beam with uniform load. And if you remember from the previous examples, and you should remember them because this is what you always will come across. See, in this example we have a combination of point load and uniform load. And so for shear, and this is for bending. So you see, for shear it was something like that, and went like that, and down like that, we said, and then like that. That was the shear diagram for point load. And bending diagram for point load was something like that, something like this. Just keep that in mind. This is P. Now for uniform load, the shear diagram was like that, and then this went up like that. That was the shear diagram. So just keep that in mind. And for bending moment, it was something like that. So having these in mind, you should always have some sort of an estimate what the bending and shear diagram for this one will look like, because what we'll do in the calculation is just to get the exact locations. So if I would do some sort of guessing based on these, I would go something like that. If this is the bending, shear will go like that and come down, and then go like that and go like that. I'll estimate. That's for shear. For bending, because of this, so it will go something like that, and because of this it will be something like that, I would assume. So just keep that in mind, because at the end when you'll be asked a question about diagram, you need to sketch a diagram. The mark dedicated for diagram is remarkable, so you need to pay attention to that part. So that's for the reaction. When it comes to the now that we calculated the reactions, we'll just update our sketch here. So for the reactions, this will be equal to 30 kips, and this is equal to 45 kips. So back to the calculation. We said we'll take a point here, a point here, a point at the 30. You can take another one at the 15 if you will. We can do this also. So we could go on the 15 also. And I'll get this as 15 feet. These are feet. Of course, as you know, for the point load, it is straightforward. So the first reaction goes by a distance of, this is 30, so meaning that this distance is, say, 30 millimeters. So this is the first point. So this continue like that until it hits the 15. 15 will bring this down by 15. So this distance is 15. Now this is at point 10. We'd like to know what is the value at point 15. So we can do this. So say shear from left at distance of 15 feet is equal to how much? So for that one, the sketch for this part will be then we have the uniform load also on top of it. So this will be, these are the distances. This is 5 feet and this is 10 feet. And of course this is 30 kips. So if we'd like to do, this will be upwards, downwards, and this is downwards. So plus 30 minus 15 and minus this WL, which is equal to, so now we get 15 minus W is 3 kip per foot and L is 5 feet is equal to, so we get is equal to 15 minus 15 is equal to 0. So meaning that at this point the shear is equal to 0. Now if we continue, the shear at 20 from left is equal to how much? Same. The only thing, this distance changes, that's the only thing. So I'm not going to sketch that, so it will be plus 30 minus 15 kips, of course these are kips, minus the W is 3 kip per foot, and the distance now is, this is the distance which is 10 feet for the uniform load. 10 feet is equal to minus 15 kips. So if I go to distance of 20, at 25 if I go, is equal to how much? Though I don't need to, because I know the uniform load will be a straight line, so if I draw a straight line that should do it. But let me just do the number. At 25 feet is equal to how much? So I'll have again plus 30 minus 15 minus 3 kip per foot multiplied down, 15 is somewhere around here, so it will be distance 15. So distance 25 will read 15 for the uniform load. 15 feet is equal to, so I get minus 30 kips. And this point should read minus 45 to be able to close the diagram. So let's see. So shear from left at a distance of 30 feet is equal to how much? Same equation, it is 30 minus 15 minus 3 kip per foot multiplied by, now this time this distance from here to here is equal to 20 feet is equal to, so I get here minus 45 kips, which is correct. So if I would like to sketch now with this diagram, so all I need to do is connect this line to, of course my sketch maybe needs a bit tweaking, and then this will go down here. So my shear diagram will be that's my shear diagram. Now we'll work on the bending moment diagram. As you can see, I selected these points to calculate the bending moment diagram at these points, and then I'll put the values here, and then I will sketch my diagram. This because this one is the distance. So let's do that. So we'll do one at a time. So we'll do a bending moment from left at a distance of 10 feet is equal to how much? So to sketch this part, I have this, and this is 10. If you will, we can sketch this one also if you want to, which is the 15 kip, and this is 30 kips, but this will have no effect, no rotational effect, because this is 10 feet. So this will rotate in this direction. This doesn't rotate because it's passing through the point here. So and this is negative, of course. So it will be minus 30 kip multiplied by 10 feet, and is equal to minus 300 kip dot foot. That's the first value. Now if we want to go to moment at the distance of 15 feet is equal to how much? Now if we do the sketch, we'll see that this is the 30 and this is the 15 kip, and here's the uniform load. So we're doing this at the following distances. This is 10 and this is 5. So back to. So of course this will rotate in this direction, which is negative. This will rotate in this direction, which is positive. And this part will be represented by an equivalent here, which is uppercase W. So we'll do that. So this will rotate, and this will rotate, in this direction, which is again is positive counterclockwise. So I have again same thing, minus 30 kips multiplied by this entire distance, which is 15. Feet. Then I have plus the 15 plus 15 kips multiplied by 5 feet, this distance only. Then this is also plus, and this will be 3 kip per foot multiplied by 5 feet, that's the distance, that's the force, and the distance is 5 feet divided by 2 is equal to. If we do the numbers, then you'll see it comes to minus 337.5, that's kip foot. That's the value. Now we'll do a distance of 20. The equation will be the same. This equation will repeat same. That will do the sketch to show you. So have, and again this is and this is the other force, and here is the uniform load, and this point is where we're taking the moments about. And this is this is 10 feet, and this is, in this case, we are doing a distance of 20 feet, so this is another 10 feet. So I'm doing this here. Moment from left, a distance of 20 feet is equal to how much? So apply the very same thing. We have, this is 30, this is 15 kip, and this will be in the middle, W. So we have minus, again this rotates in this direction, this rotates in this direction, this is negative, this is positive, and this is also positive. Minus 30 multiplied by the entire distance, which is 20 feet, then plus 15 kips multiplied by this distance, which is 10 feet, then plus W is 3 kip per foot, and the distance is 10 feet, so this is again 10 feet multiplied by 10 feet divided by 2 is equal to, and this is equal to minus 300 kip foot. Then we'll do a distance of 25. A distance of 25 feet is equal to how much? Same. We'll do the sketch, which is the same, I guess. This is uniform load, and this is the point. So if you go back to the distances, see this is 10 feet and this is now 15 feet. The rotation, this will rotate in this direction, which is negative. This will be positive. And of course the equivalent force also. This resultant will rotate positive. So like I said, the equation is again same. So it'd be minus 30 kip multiplied by this entire distance, which is 25 feet, plus this 15 kips multiplied by this distance, which is 15 feet. And we have this uniform load, which is positive. W is 3 kip per foot. Multiplied by this distance again is 15 feet. And the distance is 15 feet divided by 2 is equal to. So if we do the calculation for this one, this comes out to minus 187.5 kip foot. So these are the last one will be the bending moment at this point. Would like to prove we were using the very same of these equations, we should get 0 because the bending moment at hinges should be 0. So let's do that. I'll do bending moment at distance of 30 feet is equal to how much? So we have this will rotate in this direction, this will rotate in this direction, and this will rotate in this direction. So positive, positive, negative. Of course, the value here is equal to 30 kips. So let's do the numbers. So again, this will be minus 30 kip multiplied by this entire distance, which is 30 feet, then plus this one, which is 15 kips multiplied by this distance is 20 feet, plus W, which is 3 kip per foot, multiplied by the distance is, this is the force, by 20 feet. This is the force, and distance is from here, 20 feet divided by 2. Feet divided by 2 is equal to, if you do these numbers, you'll find this is equal to 0. Now that I have all the points calculated, so I can go and update my sketch. So if I go back to the values, this is 0, and this is 0. Let me see what other values are. And I have minus 300, minus 337. This is minus 300, and here is minus 337, and then I have minus 300 and minus 187. Minus 300 minus 187, and this is 0. And again, the uniform part will always be a curve, and this will be a straight line, so it will be something like this. And then this part will be curved like that. So our bending diagram will be